The leak integrating fire model is the and fire part we're going to address now. So we reintroduce our input to the differential equation. Input is internal or external, we'll just call it input. And we have our initial condition, the V reset. And as we know it's a linear differential equation, we know an exact solution. So now we have the solution that the membrane potential is equal to the resting potential times the input, and then some reset minus the membrane potential minus the input, and then some exponential. The exponential is the only actual dynamic part of it. So I'm just going to set the time constant to be 10, resting potential to be minus 75, minus 75 for the reset potential, constant input is 10, and resistance is 10. And so what we have here is a directed graph. We have our input, we have our internal processing, which is our time constant, and then we have our resting potential. So our solution is just something that exponentially increases and then plateaus. Now, the question you have to ask yourself is, does this look like a spike? Does this look like a neuron? And immediately you should go, no. A neuron doesn't plateau at some very positive value. It normally stays around minus 75 because it requires a charge difference. So what's happening? What do we need to do? We need to model the fire part. To model the firing of a spike, we must have a threshold. And above that threshold it fires, and below that threshold it observes the dynamics of the equation. So if it goes above the threshold, the membrane potential of VT is above VTH, then we have a spike. We should record the spike time and number of spikes. And then we reset to start again. So we have our differential equation. Our differential equation is satisfied when the membrane potential is less than some threshold. And when it goes above a threshold, you record a spike and then you reset it. And so we have the exact solution. We can solve this. Mathematically, this is kind of disturbing because it's a discontinuity. But that's what a spike looks like. It looks like a 0 or 1. And that's why we have it. So we have spike, 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 spike. We have the raster plot below, which shows spike, and just each of those dots shows when there is a spike. Because that's generally the information that people normally start with when they're analysing spike trains, when they used to analyse spike trains. There are more advanced ways now, which you'll see. And so that's for some constant input. You get spike, spike, spike. You can manipulate the input to see how the number of spikes impacts the firing rate. And this is the beginning of what's called a rate model. When you learn this relationship, you don't have to describe each spike, you can describe the number of spikes. Because a lot of analysis is done by number of spikes, not by individual spike counts. But once again, people are delving into that work right now. The leak integrating fire model has some strengths and weaknesses. It has an exact solution. That's great mathematically, very easy to manipulate. It's very easy to interpret, as in we can look at the answers and we can see what's happening. Great to build a network of models. But spiking is a discontinuity. Mathematically, that's a big, no, but it's hard to deal with. It's an abstraction from biology. You can't directly link it, but it's linkable, but it's a bit more work. The Hodgkin-Huxley, which is a bigger form of this, you can really link directly to biology. And it can't really generate different spike patterns as in a chattering neuron or all those different types. But simple extensions can. So the last two exercises you have to do is listen to the discontinuity of spike and leak integrated fire. So listen to the spikes. That's what an electrophysiologist does. So as a computational person, you should think about the sounds. And also play with the values of the input of leak integrating fire and see how it impacts the firing rate.